advanced factoring. So earlier in the course, in the pre-algebra chapter, we went through a whole section on factoring, specifically factoring polynomials. For the most part, we were factoring polynomials. And we learned a lot of techniques for factoring a bunch of different kinds of polynomials. Taking out the greatest common factor, grouping. We had a formula for the difference of two squares. We had formulas for the difference in sum of two cubes. We developed methods for factoring any kind of quadratic trinomial. Okay, but as you most likely said to yourself by the end of that section, yeah, so we could factor different kinds of polynomials, but it seemed like how far we could go with that was pretty limited. You know, when we had a polynomial with 4 or more terms, yeah, we did grouping, but it seemed like the problem was like tailor-made to be able to work. It seemed like if there was any kind of real life situation where it was just a random polynomial, most likely then grouping wouldn't work. But especially once you get past a polynomial with more than 4 terms, you know, we can't factor it. Well, in the next video, we're going to go through section 3.4, which is titled Zeros of Polynomials. And by the end of this section, and once we've worked example problems and mastered the concepts from this section, then the array of polynomials that you'll be able to factor will have expanded immensely from what we can currently factor at the moment, just from what we learned in pre-algebra. Now, I touched on this in the previous section when we talked about the remainder and factor theorems. So now that you know the factor theorem, you do have more of an ability to factor more polynomials. But in this upcoming section, we're really going to add a few additional tools that will bring everything together as far as advanced factoring. So this section is going to include the fundamental theorem of algebra, the rational zero theorem, the Descartes rule of signs, and more, which all together with the factor theorem and the remainder theorem is really going to open the door wide open for factoring polynomials. Now, I wanted to make this video before we got into section 3.4 because when I went through algebra personally, and you know, going through these sections with the remainder and factor theorem and zeros of polynomials and everything, it seemed kind of, a lot of this stuff seemed kind of pointless, kind of trivial. I didn't see the purpose of anything. And so I wish it was pointed out to me more explicitly that these tools here are, yeah, they're allowing you to find zeros of polynomials, that's important, but also allowing you to factor polynomials, right? It's building on what we weren't able to do from what we learned in pre-algebra about factoring. Okay, so now before we get into this section, I want to point out a couple of more things. So, okay, here's a polynomial, and you can think about if we were given this polynomial in pre-algebra, you know, there's nothing we can do. I mean, yeah, other than we would look at grouping. Maybe group these 3 together, get a trinomial, group these 3 together. I don't know. Group these 2 and, you know, just grouping, but what are the chances grouping is going to work? Unless someone designed this one particular polynomial to allow grouping to work. But how realistic is that? You know, in real life, if you had a 7-term polynomial, you can't apply grouping to it, right? But once we're done with this section, we'll be able to factor this. We'll have the techniques that are needed to factor this. And so, but I want to point out, though, that in pre-algebra, typically we would go to the point, when we were factoring, we would go to the point where if we had something like x squared minus 2, well, when you take the square root of 2, you don't get an integer, right? If this was x squared minus 4, we continue factoring to x plus 2 times x minus 2. Well, here, since the square root of 2 is not an integer, we would typically stop here in pre-algebra. But technically, you can continue factoring this, though. When you think about factoring in general, you can factor this because you can say this is x plus root 2 times x minus root 2. Okay, now the reason why you can do this is because this is exact. Yes, root 2 is an irrational number, but this is exact. This is exact. Okay. Now, what you couldn't do is you couldn't, if for some reason you didn't know, for whatever reason, just as an example, you didn't know that you had root 2, but you could figure out a decimal form or something, and you wrote this, you had a root 2, or you had an irrational number that you wrote as a decimal, and so irrational numbers repeat to infinity, but you stopped like here. No, you can't do this. This is not exact. This is not exact. Any factor you have, the numbers need to be exact. And so another way to look at that is we know from the factor theorem that with a polynomial we can plug in different x values to see where if that x value makes the polynomial equal 0, and if it does, we know that x minus that value, that this is a factor, right? Well, that's fine. You can plug, that's a technique, just kind of doing trial and error, plugging values into your into your calculator, or like a software like MATLAB or something. You write a code, and that's what we're gonna learn techniques in this section that allow us to be smart about the different trial and error x values we use to plug into the polynomial to find zeros and factors. But you have to be careful in that, like calculators will, if you get an answer like 1 times 10 to the minus 8 or minus 9, like it's very close to 0, then the calculator will just round it to 0, and the software will just round it to 0, which is fine for most applications. That's fine. However, for a factor, if you're trying to find a factor, then it needs to be, the result needs to be exactly 0. So that's the idea. It doesn't have to, for actual factoring, this doesn't have to be an integer. It just needs to be exact, right? So what does exact mean? Like a radical, or you can write a repeating decimal or a non-repeating decimal. You want to write that as a fraction in the factor. I don't know if this is an official math rule, but you don't want any decimals in factors, because you can take any decimal and write it as a fraction, right? Any repeating decimal or non-repeating decimal, you can write that as a rational number. And then, of course, if it's an irrational number, you definitely don't write it as a decimal. You want to put it in the like either put pi or put the radical. Okay, and then also, let's say you have a rational number, you have a fraction, and you find that a 0 of a polynomial is 3/5, let's say. Okay, and so the factor is, this is another point to note, you could put this as x minus 3/5, and that's fine. That's a factor, but it's cleaner to do. You could also write it this way. You could say 3x minus, or no, it would be 5x minus 3. You could write this as 5x minus 3. Right? So you get the same 0. So just note, you can write a fraction, any rational number, you can write kind of in an integer form this way. Okay, so if we look here, here's the fully factored form of this polynomial. There's an integer 0 there. Here's a rational 0. This is minus 7/2. Here's 2 irrational zeros. And then also note that you can have non-real factors as well, non-real zeros. Okay, so here's the if you plug in 2 plus 3i into the polynomial, it'll be equal to 0. If you equal to exactly 0. If you plug in 2 minus 3i into the polynomial, that will be exactly equal to 0. So these are factors as well.